So we want to prove that the square root of 2 is irrational. We're going to do this proof by contradiction. So our first step is to suppose the opposite. So to suppose square root 2 is in fact rational. So then, by the definition of rational, we could write the square root of 2 as a ratio, a over b, and we could keep going from there. So if I could write square root 2 as a over b, just do some algebra, I'll square both sides to get that 2 is a squared over b squared. If I were to solve for a squared by multiplying both sides by b squared, I would get a squared equals 2b squared. And then you can see that a squared is even, right? Because a squared is 2 times something, and that fits the definition of even. And if a squared is even, then a is even. You can do a couple examples of this to prove it to yourself, and I'll prove it later, but it does follow. If a squared is even, then a is even. And if a is even, then you can write a as 2 times some integer k. By the definition of integer, right? It's divisible by 2. All right, fine. So it's a lot of algebra. We got a equals 2k, and I'm going to substitute it back into this equation here. So I'll have 2 equaling 2k squared over b squared. So then I'm getting, let's come up here, 2 equaling 4k squared over b squared. And if I were to solve for b squared, just multiply by b squared, I get 2b squared equals 4k squared. So b squared is 2k squared. So I can see that b squared is even because it's divisible by 2, and therefore b is even. And now, this is actually our contradiction. And I forgot to say in the very beginning one of the most important things here. When square root 2 is rational, we can write square root 2 as a over b with a and b relatively prime. That just means that a and b have no common factors, and therefore that is a reduced fraction. So you should always be able to write a fraction as a reduced fraction, and you could write square root of 2 as a over b with a and b relatively prime, having no common factors. And that's where we're getting our contradiction. If b is even, then it's divisible by 2, and if a is even, then it's divisible by 2 as well. So they have a common factor of 2, so therefore they are not relatively prime. So this is our contradiction. So a and b are both divisible by 2, and therefore are not relatively prime. So our assumption must be false. And so our initial assumption was that the square root of 2 is rational. If that's false, then the square root of 2 must be irrational. And that is one nice way to prove it. Now I kind of glossed over this idea that if a squared is even, then a is even. So I'll just do a little mini proof of that. So you can kind of think of it like if a squared is even, like maybe a squared was 16, then a would have been 4. That's even, right? Maybe if a squared were 64, then a would have been 8. That's even. It seems like it's working, but if you want to prove it, so we want to prove if a squared is even, then a is even. We're going to start by doing another proof by contradiction. We're going to suppose the opposite, right? Suppose if a squared is even, then a is odd. Suppose a squared is even, and a is odd. Right? So if a was odd, then a could be written as 2k. This would be even plus 1 more would give you odd, right, for some integer k. And then you could write a squared as 2k plus 1 squared. So 4k squared plus 4k plus 1 would FOIL that out. And I can pull a 2 out of these and say 2 times 2 squared plus 2k plus 1. So this is even, right, because it's 2 times something, plus 1 would give me odd. So a squared would be odd. And our initial assumption said that a squared is even. So this is a contradiction. So our initial assumption must be false. So a squared is even, and a must be even. And there we go.